Hello everyone, welcome to this lecture on Lagrange Interpolating Polynomial. Suppose we are given n plus 1 distinct nodes x0 to xn and all these nodes belong to some interval I. Also a function f of x is given which is continuous real valued function, and this function also defined on interval I. The main question is how to construct an interpolating polynomial Pnx of degree n such that Pn xi equal to f of xi for I equal to 0 to n. Here we discuss two different methods to construct an interpolating polynomial. One possible approach is direct method. In direct method, we substitute each node into the polynomial. Means we substitute here x equal to x naught, x equal to x1, x equal to x2, okay, and use these interpolating conditions to determine the coefficients a naught to an. So we obtain a system of linear equations, n plus 1 linear equations into n plus 1 unknowns. Unknowns are coefficients. However, solving such a system can become complicated when n is large number. Because of this difficulty, we look for a better method, that is Lagrange method. In Lagrange approach, instead of solving coefficients directly, we define the polynomial in this form: fx naught into L naught x plus fx1 L1 x plus and so on plus fxn into ln x. And this form of interpolating polynomial Pnx is called Lagrange form of interpolating polynomial. Here each Lix is called Lagrange basic polynomial. Means L0 x, L1 x up to Ln x all are Lagrange basic polynomials. And these polynomials has a special property, means Lixi equal to 1 if I equal to j, and it is 0 if I not equal to j. Because of this special property, interpolating conditions are satisfied automatically and we don't need to solve a complicated system of equations. This form is called Lagrange form of interpolating polynomial because it is based on a Lagrange basic polynomial. Now let us formally state the Lagrange interpolating polynomial. We are given n plus 1 distinct nodes x0 to xn belong to some interval I, and a function f of x which is continuous real valued also defined on that interval I. Under these assumptions, uh, we say then there exists a unique polynomial Pnx of degree less than or equal to n, which is Pnx equal to summation I equal to 0 to n f of xi into Lix, such that Pnxi equal to f of xi. This polynomial Pnx is called Lagrange interpolating polynomial, or it is called Lagrange form of interpolating polynomial. Here the word unique is very important. Okay, it means there is only one polynomial of degree at most n that passes exactly through all the given data points. Okay, so this polynomial satisfies the interpolating conditions Pnxi equal to f of xi for I equal to 0 to n. Here Lix is defined as the product of terms with numerator x minus xj and denominator xi minus xj. And xi minus xj, this term, this denominator is constant. And in this product, you can see we skip the term where j equal to I. Clearly, Lix becomes 1 when I equal to j, and it is 0 when I not equal to j. So due to this property, this summation formula of P and X satisfies the interpolating conditions. Okay, and it is due to this property only. So here Lix is called ith Lagrange basic polynomial or Lagrange multiplier. For n equal to 1, we obtain linear form of Lagrange interpolating polynomial, that is called linear interpolating polynomial. For n equal to 1 means we have only two distinct nodes, x0 and x1, along with the corresponding function values f of x0 and f of x1. First, we define the basic polynomials or multipliers. First basic polynomial L0 x, which is corresponding to L0, we have x minus x1 divided by x0 minus x1. And second one is L1x, which is x minus x0 divided by x1 minus x0. Here you can see L0 x becomes 1 when x equal to x0. Okay, and L0 becomes 0 when x equal to x1. Similarly, L1x becomes 1 when x equal to x1, and it is 0 when x equal to x0. Now we construct the interpolating polynomial by combining these basic polynomials with the function values. So P1x we can write f of x0 into L0x plus f of x1 into L1x. On substituting the expressions for L0 and L1, we obtain P1x in this form. After simplifying this expression, we get P1x equal to f of x0 plus this f of x1 minus f of x0 divided by x1 minus x0 multiplied with x minus x0. Graphically, this polynomial P1x is simply the straight line joining two points x0 fx0 and x1 fx1. Okay, with slope f of x1 minus fx0 divided by x1 minus x0. So this is the slope of this straight line, that is P1x means linear interpolating polynomial. So when n equal to 1, Lagrange interpolation gives linear polynomial of degree 1 that passes all the given data points. Now we discuss Lagrange form of quadratic interpolating polynomial that we obtained for n equal to 2. N equal to 2 means we are given three distinct nodes x0, x1 and x2, and corresponding values f of x0, f of x1 and f of x2. For these three distinct nodes, we first define the three Lagrange basic polynomials L0x, L1x, and L2x. You can observe the pattern here. Each basic polynomial, either L0x, L1x, or L2x, each basic polynomial contains two factors in the numerator. In L0x, factor is x minus x1, means for x1, x minus x0 we are having for x2. So here we skip the factor x minus x0. So x minus x0 factor is not here. In L1x, we skip the factor x minus x1. And in L2, we skip the factor x minus x2. Okay. So this is the pattern. to define basic polynomials. For three distinct nodes in numerator, we will have two factors in each basic polynomial. Also, you can see L naught x becomes 1 if we substitute x equal to x naught. X naught minus x1, x naught minus x2. It is 1 for x equal to x naught. And for x1 and x2, it is 0. Same for L1x. L1x is 1 for x equal to 1. X equal to x1. And it is 0 for other nodes. Same for L2x. It is 1 for x equal to x2. And it becomes 0 for other nodes. Means for x0 and x1. Using these basic polynomials, we define the quadratic interpolating polynomial as p2x equal to f of x naught into L naught x plus fx1 L1x plus f of x2 L2x. Okay. Graphically, these basic polynomials, suppose we have these three distinct nodes, and this is the original graph of original function. Red dots represent the corresponding function values for these three distinct nodes. Okay, so you can see the quadratic polynomial p2x that we represent by green curve. It is a parabola, okay, that passes through all the data points, okay, means satisfy the interpolating conditions. You can see here. So when n equal to 2, Lagrange interpolating polynomial is of degree 2. Means we are getting quadratic polynomial of degree 2 p2x that passes through all the three data points. So this is called quadratic polynomial of degree 2. Now we solve a complete example using the Lagrange interpolation process. We are given the following data. That means we have four distinct nodes 0, 2, 3 and 4. Corresponding function values are 7, 11, 28 and 63. Since there are four distinct nodes here, the least degree polynomial will be of degree less than or equal to 3. Means we expect a cubic polynomial here. Using the formula Lagrange interpolating polynomial that we denote by P3x. It is f of x naught into L naught x plus f of x1 L1x plus f of x2 L2x plus f of x3 L3x. Okay. Now let us construct the Lagrange basic polynomials first. So first we find L naught x, that is corresponding to x naught equal to 0. So we multiply the factors x minus 2, x minus 2, x minus 3, x minus 4. Three factors, and divide by the constants 0 minus 2, 0 minus 3, 0 minus 4. Means in numerator just we put x equal to 0. Okay, after simplifying we get L naught x equal to x minus 2, x minus 3, x minus 4 divided by minus 24. Similarly, we find L1x, L2x and L3x. Okay. Now we get P3x as 7. 7 is the function value. 7 L0 plus 11 L1 plus 28 L2 plus 63 L3. Okay. After simplifying all terms carefully and combining like terms, we obtain the final interpolating polynomial P3 as x cube plus 2x square minus 3x plus 7. This is the required cubic polynomial of least degree that satisfies the given data values. So friends, if you found this lecture helpful, please like the video, subscribe to the channel, share it with your friends, and if you have any doubt or question, write them in the comment section. Thank you very much.